So the first thing that I wanted to discuss is the question that popped up yesterday, and actually I didn't even have to look up the answer. I just had to think a bit harder. So the question that popped up yesterday is what happens if you have these two learners. So in Paxos, the acceptors send a message to the learner as soon as they know that this is an accepted command. And the question was, what happens if not only this message is lost, but this message is lost as well? Which would mean that this guy would not see a majority of acceptors, and only this guy would see the command to be executed. Welcome to class. So, then what? And the answer is kind of obvious, but I overlooked it.
It just doesn't get executed.
No, it gets executed. Learner number one will execute the command. Hi. And in fact, you should know the answer. That's a hint. So yesterday we had the situation, like if you have a fault-tolerant group working under arbitrary failure semantics, and one of the members fails, then you move from 2k plus 1 to 2k, and then let's assume you get 2 answers back saying yes and 2 answers back saying no. And you said something that was very wise. Your observation was, you're not sticking to the basic assumptions, if I rephrase your remark. You're saying, well, you could tolerate only k failures. In this case, k was 2. But what you're seeing is not 2 failures or 1 failure. You're seeing 3 failures. Okay? Now let's go back to this example. If it turns out that also this message is lost, effectively disabling this guy, what is the situation that we're in? We're not having 1 failure, we're having 2 failures, and that's not what Paxos is supposed to handle in the case of k is 1. So what you now also see is that indeed Paxos will require 2k plus 1 servers to tolerate the failure of k servers. And of course I could have come up with this answer yesterday, but I'm glad it took me some thinking to come up with the correct answer. Does everybody see this? So the command will be executed, but hey, you're in exceptional mode here because all bets are off because you're not working under the normal assumptions anymore. Okay?
If you open 3 nodes account, then the equation on the first node is going to be executed.
If all 3 nodes are cloned?
If you open 3 nodes.
If 2 out of 3 are doing what they're supposed to do, namely execute the command, you're in good shape. Because essentially what then is happening is that you're tolerating the failure of 1 server in this case. So this situation is according to specifications. Okay? But as soon as you lose this message, you're in a situation that the whole algorithm is not working under the initial assumptions anymore. And that was something that Paxos was not built for.
In such cases, is the operation first node going to be executed?
It will be executed.
Yeah, but the assumption would be that you don't know what happened because you have 2 nodes that are known.
So this is again an interesting observation. We're building a k fault tolerant group. We have more than k servers failing, and basically, you will get an outcome, or may not get an outcome. But the whole issue is that you weren't expecting anything other than garbage. And maybe by coincidence something's going okay, but you can't rely on it anymore. If only one server fails, in this case, technically the middle one, then you see that still two are producing the right results, and by a voting mechanism or whatnot, you can actually decide on what the actual execution should be. So in the end, what will happen is that these two will produce a result, and let's assume they produce the right result. You know that that will be the result. And otherwise, you may pick up a result, but because this is one big black box to a client, you don't know. Welcome to the world of failures.
I have one more question.
Yeah.
What is the logic behind sending an accept message with your proposal number and not with the highest proposal number?
What is the rationale behind sending an accept message with your proposal number and not the highest proposal number?
Because you might get in a case that you can obtain a majority from the acceptors, but because one of them has an operation, a command that belongs to a lower number, a lower proposal number,
Yes.
you won't accept your command. But from the part of proposers, they may all be in the same agreement.
The proposers will not be in agreement. The issue that you have here is the following. The acceptors are in a state in which they had accepted a command. Okay? That's a fact of life. And different commands may have been accepted by different acceptors. And what is essentially happening is that the proposers, no, not the proposers, that you're going to use a proposer to effectively tell the other acceptors what the command is that they should execute.
Yeah, if all proposals have the same command but different proposal numbers,
Yes?
then you may get in a situation that one acceptor that has another command but lower proposal number, not to offer you, not to execute your command, basically.
Hold it. If, let me try to see if I can repeat this, your observation. So if you have multiple proposers with the same commands but different proposal numbers, then your claim is?
My claim is that one of the acceptors may have a operation, another
Ye-
operation that now the proposer have.
Yes?
But
So let's say all the proposers propose X.
But a higher proposal number that it may receive from one of the proposals, one of those proposals that have a lower proposal number.
So let's just try to make this concrete as possible. Let's say that all proposers want to have command X executed by coincidence, okay? But they use different proposal numbers.
Yes.
Yes? Okay. So far, so good. If
No, I mean.
no,
After the acceptors send their promises,
yes,
they all get into the same command but different proposal numbers.
yes, that is possible.
That is possible, but it's also possible that one acceptor may have another command and a higher
Yes.
proposal number that
Yep.
one of the nodes has.
Yep. Tough luck.
Tough luck to get.
Tough luck. Because the algorithm focuses on the commands that should be executed. It couldn't care less on what the proposers agreed, quote unquote, because the proposers haven't agreed anything. And the issue is that the acceptors are trying to accept commands. And essentially what is happening is by sending promises back to a single proposer, that they're using that proposer to force a majority of the acceptors to go for the same command. So instead of letting the acceptors all talk to each other, this is kind of my view, that they misuse a proposer to impose the same command on the majority of the acceptors. Now, the issue that pops up is, is this fair?
Yeah, is this fair?
No, it's not fair. Okay? And what I'm skipping over, all kinds of things, is, for example, that you can actually enforce a proper ordering of the commands by installing a leading proposer. And a leading proposer essentially hands out sequence numbers to proposed operations that come from a client. So basically you will have all clients talk to the same leader. That leader will hand out tickets for commands, and then you will see that every command will eventually be executed. That's progress in Paxos, but I've ignored that. Okay? So, and what I'm also ignoring is a multitude of optimizations in Paxos to really speed this thing up. Yesterday after the class, I noted to people that if you would just implement exactly the algorithm that I've discussed over here, you would see command by command by command, one after the other. That's practically not acceptable. So what you do in a practical implementation of Paxos is that you run, and I mentioned this yesterday as well, multiple instances of this protocol in parallel. And that just complicates matters but doesn't affect the essence of Paxos. And you throw in leaders to make sure that you can have progress. But then, the next thing you could ask is, what if you suddenly have two leaders? Well, then you have a problem that needs to be solved. And I'm skipping over all those gory details. Okay? Yes? The proposers are not talking to each other. How do they know the number to get? By magic. And I hinted at the magic when I was talking about, wait a minute, let me see if I can move to that slide. It's way up here. Is it this one? It's this one. I hinted at that solution by saying that you take a proposer, it has a counter, okay, that is n higher, this should be m, higher than any of its previous counters, and I'm talking about the proposal numbers as this pair, m comma y. That's how I can do a uniqueness, but there are other ways of establishing unique proposal numbers. That's really an implementation issue. But you do need to guarantee this. Okay. Then there was another question from you yesterday about the operations. So what I did in this simplification is that I let the acceptors, simply send out a learn X. You could change this by also adding the proposal number. And then you're in a better position to distinguish among different commands that need to be executed. And I haven't looked it up, but then you could probably do the optimization that you suggested. But although you would need to take the proposal number into account.
It is right now, the third one is losing one message.
This one's losing one message, yes?
The third acceptor sends out its three messages, but one is lost.
One is lost, yes.
If the second one would lose its message to the third learner,
This one?
yes, and X would not be executed on the third one.
Then X would not be executed on the third one.
Each acceptor only has.
Yeah, so let's say that this message is lost as well, okay? Then this guy over here would see only this message and would not execute the command. And to come back to the question that your neighbor posed yesterday, what happens if only a single learner will actually get this value X to learn? Basically what is happening is that you're having more than K failures, K is 1 in this case, which means all bets are off.
Is it one failure for the system, for the whole system, or one failure per acceptor?
No, so the issue that what is a bit nasty about these examples is that I only concentrate on lost messages. Okay? What I should do is concentrate on failing servers, even also in their roles. But it also works with the messages. And the essence is that even if these two guys send their messages, and the simplest case to explain this is that even if this message is lost, then basically you're having too many failures in the system such that you're violating the initial assumption that K, that you're having more than K is one servers fail. And I have to do this a bit like quote unquote because I'm focusing on messages instead of servers. But I hope that the idea is clear.
In the system that failed earlier, between proposal and acceptors, there was also more than one failure.
You mean in one of the previous slides? Yes. So in that case, it still worked. So this is a kind of a corner case, but your system is allowed to work correctly with more than one failure, but you don't have to provide the guarantees that it works. That's a subtle difference. But in principle, all bets are off when you have too many failures. That's the bottom line. Yes?
So K doesn't tell anything about the number of lost messages then?
No, but I'm explaining this example here, and this is where the analogy goes wrong, because I should be talking about failing servers, and then it would become more clear, and you would see more than one failing server. But I can explain it in terms of the messages that are lost.
It's not the same thing.
No, it's definitely not the same.
One failing server, one server doesn't receive a majority of messages.
So let's do it differently. This is now this mouse. Okay, this is now a partial failing multicast, and to make it strict, I should actually have this guy over here fail, so there won't be any messages whatsoever. That would actually be more clear. And I will reconsider this example to see if I should explain it along failing servers. Okay, but I hope that the basic message is clear, that there are too many failures and that you're violating your initial assumptions. Okay. And then let's go to the next slide. Okay, I have two more slides on failure detection. So the issue is, how can we reliably detect that a process has actually crashed? The general model here is rather simplistic. You let a process be equipped with a so-called failure detection module. And there's nothing fancy about this. This is just a thread saying, are you alive? Are you alive? Okay, but we call it a failure detection module. And what you essentially have is that a process P probes another process Q for a reaction. That's what failure detectors do. And there are lots of papers, theoretical papers on failure detectors, but in the end, even as I write in the second edition, they just send messages and they start a timer. And if they don't get an answer back, hey, you're assumed to be dead. Okay? So if the other one reacts, then hey, you're happy he's alive. If he doesn't react, then basically you're being suspected to have crashed. Now the word suspicion here is important. In a synchronous system, a suspected crash is a known crash. I hope that's clear. But like I explained, there's no such thing as a synchronous system, but perhaps partially synchronous systems. So this is really the case of a perfect failure detector. And what you have in practice are eventually perfect failure detectors. And that eventually comes from the fact like, oh, I am generally operating in a kind of a synchronous mode. I may have to find out what the right timer value is, and I'll explain that in just a minute. But hey, if it's really beyond anything that's reasonable, we're going to get the failure cops in. Okay, but then you're working in a different mode. So eventual failure detector has two important properties. It's strong completeness, very important, if every crashed process is eventually suspected to have crashed by every correct process. So in essence, this comes very close to the example I had yesterday, which was stronger, but you know, P2 and P4 Was it P2 and P4? No. Yeah, P2 and P4, because P3 crashed, yes. P2 and P4 both eventually should know that P1 and P3 crashed. Okay? So that's an important one. And eventual strong accuracy means eventually no correct process is suspected by any other correct process. So if P4 is slow and P2 is thinking, what the hell is wrong with P4? Then eventually P2 will discover, oh no, I was mistaken. P4 is still alive. And this is what you will actually see in practice. Okay? Which means that if you do conclude at a certain point that things are wrong, you can never know for sure, but hey, it would be an exception to the rule. Okay, so you may be wrong from time to time, but you treat that as an exception. And the implementation is very simple. If P did not receive a heartbeat, a response, from Q within a certain time, P suspects Q. Q turns out to be alive and kicking. It stops suspecting Q. I'm seeing what's happening with this mouse actually. And it increases its timeout value. So here you see an example of, T was too small. Let me just increase it to something reasonable. And a day is not reasonable. Okay? If Q did crash, P will keep suspecting Q. That's the whole issue. Okay? And that indeed works. I just want to test for sure that it's recording. I guess so. It's recording. Fantastic. Sometimes I do edit the slides a bit. But I think there's still a lot of garbage in my recordings. Yes?
But if you, for example, make the process to kill the process which is suspected to be crashed, you can make the suspicion react.
If you kill the process that you suspected to crash, have crashed, stick to that question until I start talking about recovery at the end of this chapter. And what it boils down to is that deliberately, let me phrase it like this, deliberately crashing, if they had not already crashed, suspected processes is going to save correctness. It's a kind of a drastic measurement, but it will happen. And then, okay, now I see your question. That means that if you have processes that still suspected that want to be crashed, they will remain suspected. But then you have to start telling people that that specific process is no longer alive. And that basically means that you'll be moving towards a new installment of a group view. Because not everybody is probing all other processes to see if they have failed. Only a selected set of processes. Namely, for example, the ones that were forming a group with them. Okay? Okay, I want to switch to reliable communication. So what I did so far was concentrate on process resilience. And do you notice the mouse? So that's interesting. This mouse will now keep alive, but this is a PDF document and the other one is a PowerPoint document. I just discovered this. This is, again, stuff that I should probably filter out during the recordings. Anyway, so I want to concentrate now on reliable channels, which are important for distributed systems. We all know about reliable channels. All of you know about error detection, error correction. This is the fundamental issue in computer networks. What you can do with error detection is you add a number of bits, and you detect, for example, that a bit has been flipped. You don't know which one, but the CRC is just wrong. And, for example, you can go for a retransmission. And the error correction, that's actually part of the retransmission, but you can also add so many redundant bits that you can identify which bit has been flipped, and then you flip it back again. Hamming codes do this, for example. I will not ask any questions about this. I want to talk about something much more important for distributed systems, reliable remote procedure calls. And you will notice it's very difficult to make them reliable. In fact, You should know by now that it's impossible. So there are 5 situations. The client cannot locate the server. That's kind of stupid. Okay, the client should be able to contact the server, so just report back to the client where the server is or whatnot. Just try it a couple of times. Okay, so that's kind of stupid. The client request is lost. Okay, you just resend the message. You should get into alert mode here. Okay? And the alert mode would be, how do you know that the client request was lost? You don't. Then there are 3 other cases that I want to discuss, and they all, in the end, will boil down to the same thing. The server crashes, okay? Or the server response is lost, or the client crashes. Client crashes is actually also kind of nasty. So let's assume that the server crashed. So the situation is like this. I'm a client, I'm talking to a server, I sent a request, and I got something back, or I didn't get anything back, but I do know that the server crashed and perhaps recovered. So the normal situation is like this. I send a request, the server will receive this thing, will execute the associated command, and will send a reply back, and I get the reply. The situation I want to look at is I send a request, and now I may have the following 2 situations. The server received it, executed, and then crashed. I detect that something went wrong because I didn't get any response back. Okay, no reply. Or what could have happened, the server received my request, crashed, and never got to the execution of the associated operation. In any case, for me as a client, I just don't get a response back and I don't know what happened. Got it? That's a problem. And I can't distinguish the 2. So we need to decide on what we should expect from the server. And here's really bye-bye full transparency. You just can't do this. So you can have at least one semantics. So you can build your distributed system that the server will guarantee will carry out an operation at least once, no matter what. Okay? Or at most one semantics. The server guarantees it will carry out an operation at most once. And now you know what I'm going to ask. Which one is better? And after so many classes, you know, well, it all depends. Because if you have a pure read operation, asking the server to guarantee at least one semantics is actually a good idea. It will help you. You know, hey, I know you crashed, but you know, it's a pure read operation. You're not going to change anything. Try it again. If you had a write operation, and that means you're transferring money because that's always the example that hurts most people. And it's not, who cares about $1? Let's transfer $10,000. Okay? At most, one semantics is fine by me. And then you'll see what happened with your money, and you'll go to the bank and say, hey, where's my money? Okay? But you don't want the server to repeatedly try and try again to transfer your $10,000. Not a good idea. So when you're designing a system, you'll have to take this into account. Okay. Now the server response is lost. You don't know. Okay? You don't know what happened. So detecting a lost reply can be hard because it can also be that the server has crashed. You can't distinguish the situations. Now what you could do, and this comes close to at least one semantics, but there's a subtle difference. What you could do is, I can try to make all my operations idempotent. That means that if I'm a client, and here's a subtle difference with what I just described, if I'm the client and I suspect something went wrong, I send the request again. Okay. Now this is different from asking the server to provide at least one semantics. Can you tell me what the difference is? Yes?
In this particular case, we have assumed that server has already executed and
Yeah, so the difference, you're saying that in this case, we know that the server executed the operation, and in the previous one we didn't. That's a false statement. You do not know that the server actually executed it, right? It just happens that I'm treating this case that the server response was lost, but I, as a client, would I see it? So I'm testing your assumption. Do I know that the operation had actually been executed? I don't. Tessa.
So you're basically trying to make sure the operation is carried out once, so not at least once, but once only. And you could do that, for example, by transferring the 10,000 only if the amount on your account is still the amount you thought it was.
Okay, you're getting very close. I'm not quite sure if I can repeat this. The one fundamental thing you said was, I'll rephrase basically something that you said, the client is in control. And you said, well, wait a minute, maybe you can modify your operation in such a way that you can carry it out a couple of times. Do you have an example? The transactions is a kind of a nasty example, but maybe you have another example where you could do this. So let's think in terms of a write operation.
Removing an item?
Removing an item is definitely, let's think about this. Removing an item is a good example. It's a write operation, okay? But it's not just removing an item. Be a bit more specific. For example, I'll give you an example. Remove the last item? No, why not?
Remove a specific item.
You have to remove a specific item. So basically, if you tell the server, do exactly this, with no context, okay? You can compare it to someone to stateless. This item, remove that one. Well, you know, the worst is the server could say is, well, I already did this. Why are you asking me again? Okay? No harm done. So basically, it's an overwrite operation. Now, what I'm telling you is that in many cases, there are many of these examples. So basically, write operations, if they are overwrite operations, they are idempotent. This is easier said than done. Years ago, we were building this hierarchical location service I was talking about. And we were doing this, I was doing this together with a colleague of mine from Germany. And our first efforts were, okay, let's write things to disk and then recover it and whatnot. And at a certain point, we said, no. Let's try to make the whole hierarchical location service based on idempotent remote procedure calls. Like, insert this pointer, insert this address. And all the insert operations were overwrite operations. So if you hadn't done it before, do it now. Have you already done it? Well, okay, good. Glad that you already did it. You can do it again. It's not going to do any harm. Turned out that we could build the entire hierarchical location service with only idempotent operations. It took us months, by the way, because it requires very careful design. Think, for example, of a read operation. Most read operations on a file are actually write operations. You read data and you advance a file pointer. That's a write operation. As a side effect, you also read some data. So if you can carefully design a system that all operations are idempotent, you're in a really good position. Because basically, servers can crash, recover and whatnot, and you just say, I think something went wrong. Here, do it again. No harm done, and you'll get a very robust system. But you can't do this for all systems. An add operation is going to be a bit difficult, right? So unless you can transform that operation and do this and write the result of the add operation. Okay? You get the picture? That's an idempotent operation. Yes?
How does it realize that which part of the server crashed, for example, in the receipt or in the execution?
Okay, so it's very important that, I'll try to rephrase your question. How
How can we understand?
How can we understand what went wrong at the server. Okay? And my answer is you can't. You just don't know. These are the situations that can occur, but can a client distinguish between these different situations? Unfortunately, it cannot. So the question then is, can I design my interaction with the server in such a way that I do not need to know? And this happens with overwrite operations. I don't care. I don't even care if something went wrong. And if something went wrong, I don't even care what went wrong or when it went wrong. I can just do the operation again, and it will not affect any good results nor any, call it bad results, a result that wasn't there because the right operation didn't take place.
So we just care about the crash that comes from the server.
In the end, because the client only sees, hey, I'm not getting a response back, it should react to the absence of a response, preferably with an operation that cannot do any harm. A transaction is very difficult because it involves two write operations, or actually more, you could argue, and doing that in an idempotent way is kind of difficult, unless you make the client completely responsible for the execution of all the operations in a transaction. Then it could fly, but then, hey, you don't have a transaction server anymore. Yes?
So why can't we have the same solution for previous situations? Because client cannot do anything, so why are we distinguishing between make at least one point?
Okay, so why, if this is what we should do, why would we bother about at least one semantics or at most one semantics? If you can get into a situation, I'll translate you. If you can get into a situation where you do not have the client, there's no necessity to let the client be responsible for the proper execution of a command, let the server do it. That's part of your distribution transparency. And it's just like I just said, in many cases, it's not even possible to define only idempotent operations. The transactions was an example. And you do want to have a transaction server. And if you have a transaction server, you tell this server, you can do your best, but at most once. If you crashed, let me know. Bye-bye transparency, but that's the best thing. And that's indeed your reasoning. Don't put what you can leave out from the clients. That will be best, because that's the task of a distributed system. Yes?
Can we say that solution 3 is implemented at server side and solution 2 is at client?
Solution 3, so either the two types of semantics. Whoops, where is it? Oh, this is interesting. How do I get back, actually? Oh, here it is. This is a server-side solution, absolutely. This is a client-side solution. Well, it's a design solution, actually, but it's the client who executes the thing. Now, a client can also crash. Ah, that's really bad. Sometimes it's actually really, really bad. You all know this. Many of you are running Linux, right? Or Ubuntu or whatever variant of whatever. So when you do updates and something goes wrong, it could be like, hey, you better check your DKPJ because apparently somebody's holding the lock here. And what you do, if you're geeky enough, you go kill the lock or remove the lock or whatnot, okay? Basically, you're recovering from a client crash because there was a process that didn't complete, for whatever reason, and it left some stuff behind, notably locks. So that's the nasty thing about a client crash. The server doesn't know what to do, and the clients may actually have forced the server to, for example, install a lock. So the problem is the server is not doing work and holding resources for nothing, and that's called an orphan computation. The server's working, but not for somebody, because that somebody was the client who crashed. Okay? So what you can do is you can kill the orphan. Yeah. Sorry about this. This is a phenomenon where you see that systems people, how shall I put this one? I have to remove this from the recording. Here's where you see that real systems people, they don't know too much about society, okay? they work in their black holes and whatnot, dark holes. But the terminology is indeed you kill the orphan process, you kill the server, okay? Or you have to roll it back. And you may have to roll it back because simply killing the server is not going to help because of those locks that are now, for example, implemented by means of a lock file that's now there. And hey, you can't pass that lock file. What you can also do when you as a client come up again, you broadcast a new epoch number. And basically what it says is, oh man, I just crashed, but I'm alive and kicking again. I'm going to start a brand new life. Okay? And then the server picks this up saying, oh, okay, let me throw away what I was working on or clean it up, and then let me join this guy in his new life. And what you can also do, but this is not realistic, require computations to complete in T time units. And then the old ones are simply removed. How do you specify T? Too bad. You know, I have this age that when I was doing my PhD, I actually had to submit jobs to mainframe computers. And I was running big simulations, and you had to specify how long your simulation lasted. And you know, this CPU time was really expensive. It's so frustrating that you come back the next morning to the lab to find out that your time specification was not appropriate. You get charged, but you see 0 results because your job did not complete in T time units. Okay, so you now know the answer to this question. What's the rolling back for? You have to clean up the use of resources. Yes?
But in the real-time systems, we know how much to do.
In real-time systems, that's a very good remark, actually. In real-time systems, you are supposed to know how long something would last, and then the time specification could work. I would claim that most real-time systems are soft real-time systems, and even in those cases, specifying T is pretty difficult. Okay? Okay, reliable multicasting. This is something that you need in distributed systems. And the idea is relatively simple. You have this multicast channel C, and I'll simplify it even more than what I wrote down here on the slides, with possibly overlapping groups of senders and receivers. I say this overlapping groups because you already know this. When I was discussing Lamport multicasting, you sent not only a message to the other guys, but also to yourself, okay? And that message was then placed into a queue, and then you simply waited until your message was at the top of the queue, and you had received messages from all the others before you could actually hand it off to the application. So you were sender and receiver at the same time. So you have a sender group of senders, processes that submit a message to this channel C. This is the abstraction. You just send with IP multicast, okay? And you have a receiver group that is supposed to receive this thing. Now, when you talk in terms of reliability, you can talk in terms of simple reliability or atomic multicast. The simple reliability is that this is actually a kind of a sloppy definition. If you were a receiver at the time that message M was submitted to the channel, and P does not leave this group, M should be delivered to P. Now, by now you should know how sloppy this is. Okay? It starts with at the time. Yeah, sure. Are we going to measure this? I'm afraid not. But the idea, of course, is like, okay, let's assume everything's very static, nobody's crashing and whatnot. And if I now multicast a message to 10 other processes, and they're still up and running while that message is in transmission, they should all receive this message. That's the whole idea. Guaranteeing this is very difficult, if not impossible. This one is more important, or more precise, I should actually say, an atomic multicast. How can we ensure that a message that has been submitted to this channel is delivered to a receiving process only if that message is delivered to all members of the recipient set? Okay, now I'm coming back to the discussion we had yesterday, where P2 and P4 were the only ones alive. They could not make any progress. What should they do? They should agree on who are actually group members, who are the recipients. Once they agree to that, then they can take the decision on which messages to deliver, right? Because then they can check whether they've received all messages from all members. And basically, they just reduce the group, and then, okay. Now, yes. Let's first take a look at a simple implementation of reliable multicasting. If you stick to a local area network, reliable multicasting is easy, quote unquote. It's actually quite simple. You let a sender log messages that is sent to the channel, and if it sends this message, that message is stored in a history buffer. And now you see what can happen. If somebody didn't receive it, comes back to you, hey, I didn't receive it, okay, I still have it in my history buffer. So every receiver acknowledges the receipt of that message, and it requested retransmission at P when it did not receive that message. Of course, it has to notice that it didn't receive that message. How could it notice this? Oh, no vector clocks. You could do this much easier. So you can do timeout, yes. You will definitely, by the way, need timeouts. I would even simpler. No crashing. Sequence numbers? And you get sequence number 1, 2, 4. 4? Wait a minute, where's 3? Go back, ask for 3, etc. So with sequence numbers, you can do a lot. And maybe you'll have to wait until you ask for 3 again, or you can do this instantaneously. So this is exactly what you do with TCP sequence numbering. Wait a minute, I acknowledge that I received the following. I'm missing something here. And you're not even doing this with sequence numbers, but you do this on sets of bytes. I came to this point. Why doesn't this scale? Nah, a buffer full. Nah, come on. You just attach a 2 terabyte disk. That's a pretty good buffer. If that's not enough, hey, take a 4 terabyte disk. Well, you get my point. Why doesn't this scale?
But everyone has to acknowledge the reset. So you're going to wait for quite a long time to know that everybody has acknowledged.
No. But you're getting close. Maybe you actually are right, but you're not formulating it correctly. When I ask a question about scalability, what should you do? Think big. Who said that? Very good. So think big.
So if you have let's say 10,000 servers, each sends one message, so then you get 10,000 times 10,000 acknowledgements back.
So here you are. Let's think big. 1 million. Now here I am, this poor client. Hi guys, got a message for you. You're dead. You'll get hey, I got it. That 1 million times, you're dead. Okay? There's no way you can process so many incoming acknowledgments. So that's a problem. So this doesn't scale. Now, I should mention that in the book, I explain a couple of schemes on how you can achieve this scalability, and to be honest, none of them really scales. What you should do is actually you could go over some of these implementations to get an idea of how you could make this reasonably scalable. And what you'll notice is that all of these methods actually scale. And there's actually one method that's called scalable reliable multicasting. And it took people a couple of years to discover that the word scalable was not what it's supposed to be. It was not scalable at all. But I'm basically suggesting that you should know a bit about this simple form of reliable multicasting, and that's it. I'm not going to ask any nasty questions about this. And in fact, what I'll do right now is let you guys have a break.